So hey guys, welcome back to another lecture. So in our previous lecture, we have a great detailed talk on this PDFs, PMFs and CDFs we have. So today we're going to discuss something known as the histograms. So the histograms plays a vital role in the visualization. Okay, so in a visualization of graphs and etc. In a visualization part in our machine learning. Okay, so histograms, so it is used to summarize the data. So why we use the histogram? It is used to summarize the data both in continuous and a discrete variable. So it is used in a continuous variable and as well as in a discrete variable by showing the number of its then fall in a specific range. So what do you mean by this specific range? Means like, so like this 5 to 10, this from the 5 to 10 range, we have a 10 students, we have a 10 students who passed the exam. So like we have a 60 to 70 marks. So in this range we have a 20 students, and we have a 20 students, and this from the 85 to 90 we have only 5 students who scored that. I hope you having basic understanding. Like, so this is a one bin, this is 60 to 70 is a one bin, and this 85 to 90 is another bin. Okay, by showing the number in that falls in a specific range. So here it means like it's showing a specific range from like here we have a 30 to 40, 40 to 50, 50 to 60 and 60 to 70. Here we have a specific range, and we're going to have these numbers, right? So like the bin range, so generally the bin range like the 10, 15, 20, 25, 30, etc. So like we have a given histogram out there. So what it tells, so here the customer, so what is this histogram? So here, so the problem is like here the customer is waiting to get the bill. So here the customer is waiting to get bill, but like we're going to summarize that how much time the customer is waiting to get a bill. So we're going to get the average time that every person is spending to get that bill. So like the number 5 means like the number 5 which is waiting almost like a 35 to 40 seconds out there, and the number 6 which is almost waiting around like a 65 55 seconds, and the most of our customers here falling under the falling almost like a 60 seconds, which is almost one minute. So we can conclude from the histogram, we can say that by summarizing, the most of the customers has to wait like from 55 to 60 seconds, which is almost as 1 minute. Means like the customer has to wait 1 minute to get the bill. This is the average. This is the average time to get the bill for any customer out there. So bin is a range of values that is used to divide the data into smaller groups. So here we have a large data out there, and we simply divided these data into small groups for the purpose of counting, plotting and analyzing. So by the help of these histograms, we can conclude that we summarized what? We summarized that the average wait is 1 minute, right? So with the help of these histogram, I hope you have a basic understanding about the histogram. So after that, we're going to cover the density plot. So like what is this density plot? So density plot is also known as the kernel density estimate, which is KDE plot. So it's a graphical representation of a distribution. So it is a graphical representation of a distribution of a data set. So like it is a smooth version of histogram. So this is a smoothed version, is nothing but, so this we have seen the histogram, right? So if we draw this line, this is a smoothed version. So we're gonna mainly focus on this line now, not the other these bins. Okay, so we're going to mainly focus on this line, which is a smoothed curve, right? So the smoothed version of histogram, which is a way to estimate the probability density function, which is PDF of a continuous random variable. So I just give an example, like so here, so we just simply plot the histogram, and then we simply have a density plot over there. So this is a smoothed curve, which is our density plot. So after plotting the density plot to our histogram plot, so how it will be? So we just simply remove these two. we just simply, so after plotting this, we simply remove these bins. We simply remove these bins, and how it will be, so like this. So how the plot will look like this. So this is a area under the curve. We have seen in our previous lecture what is this area under the curve. So this is a task for you, like, so what is the area under the curve? So this is a homework. So just mention the timestamp and comment down below. So what is the, so like what is the area under the curve, right? So this is a task for you. Okay, so we just simply find that area under the curve. We will conclude our conclusion. So we will summarize the data. After that, we will summarize the data about what we get over there. So like we have a, so we have 2 points over there, which is a and b. Then the a, which is less than or equal to x, and it is less than or equal to b, which means like it is not, if we take that, if the x is not greater than b and then not less than a, means like we have seen an example, right? So it is not -1, which is not minus, and it is not greater than 1, right? We have integral, which is p of x and dx, and we will find that area of the curve, which is our integration, right? Oh, I said the answer, so, but no worries. Okay, so I hope you find that. I hope you find that answer. So on the x-axis follows the time and range. So here the time and range of that property, of that problem. Okay, so we have a property out there. We have an integral p of x d of x is equal to 1, or every p of x is greater than 0. For every p of x which is greater than 0. I hope you having a basic understanding like what I'm trying to convey, like. So after that we have expected value. So what do you mean by the expected value? By the word you can understand, we are expecting something here. Expected value. So like what are my expected marks in the maths? These are the 90 marks I am expecting. But in reality we get only 45, 60, 80, etc. These are the expected marks, but in reality we get here. So it may be related. So if we expect 90%, but we may get 95% here, right? It depends upon the hard work you have done before the exams. Okay, so the expected value of a random variable is a sum of a product of a value of a variable and its corresponding probability. Means like, so it is like it's just a measure of a central tendency of a probability distribution. We have covered this central tendency, right? I think we have covered. No. We're going to cover in our next lecture. Hope so. We're going to cover. So we're going to cover these central tendency in our next lecture. So the expected value is just a measure of that central tendency, means like which is mean, mode, and median of that probability distribution, is also known as the mean of that solution. So like as of now that I don't know that it will be understandable or not, but I will try my best to get you understand. Okay, so it can be calculated using the formula, which is summation over rho here, and we simply multiply with the p of x. Means like where the x is the value of a variable, and the p of x is the probability of the x occurring. I hope you understanding. So if the x is a variable and the probability of that variable, which is like, so we have x is 1 and the probability of that variable is 0.5, and then we simply multiply these two. This is our expected value, right? So there is a lot of difference between the mean and expected value. So they might look similar, but they are not similar. So there is a lot of difference between the expected value, expected error, and the mean. So the average value we expect before calling the data, means like before calling the data. So it is the average value we accept before collecting the data. Means like before collecting the data we accept some value. So that is a expected value. And the mean is typically used when we calculate the mean of the sample. We have seen this, right? Some of the numbers by the number of, right? So we have seen this, the sum of all numbers by the total number of numbers. We have seen this mean, right? I hope you have a basic understanding like what I'm trying to convey to you, right? So like how we calculate these expected value, we are expecting something. We are expecting 90%. So how we calculate this 90%? So we just simply, how we calculate means like, so it's just a guessing, right? So I guess I will get 90%. So like it is for example in a stock market, so the probability of 80% of making profit is $10, and the probability of 20% of making a loss, which is $5, means like we just simply like, so this is a, we have seen this is a variable, and we have a probability of that which is 0.8, and then we have seen that right here, we just simply multiply that, and with the $5, with the $5 also, we just simply multiply this with the 0.2, and we will get our output like this. So ignore that, this is a plus only. Okay, so 8 minus 1, which is 7. So what is this 7? So this is 7 means like, means the company expected to make a $7 for each share they sell. So this is a expected value for that the stock market. Okay, I hope you understand by this example. I hope so. So like we are expecting some kind of a value. Okay, so the probability of 80% of making profit, so like 80% of making profit, which is $10, and the 20% of losing, which is $5. So we gonna expect some kind of value from these two, and that value is $7 means like the profit of the company can expect to make a profit of $7 for each share they sell. I hope you understand this example. So like how we gonna calculate the mean? We have seen, right? So we have seen the difference between the mean and the expected error. So expected error means before collecting the data, and the mean is typically used as we collect the mean of the sample, right? So how we calculate the mean? So we have seen, right? We have seen the mean of the sample right here. We're going to discuss in a great detail in our next lecture. What is mean, mode, and median. But as of now, like, so the law of large number implies that as we increase the number of experiments, our x will come close to the e. So we have seen the law of large numbers in a previous lecture. We have seen here, right? So we have seen the law of large numbers here, right? So if you run an x number of if I run an experiment in x number of times, then it tends to get the average mean, right? So if we have a mean out there, and then we simply find the answer, which is like, if we have if you roll a die, which is unbiased and an independent variable, if we roll a die, and then we're gonna get our value as a, we simply taking the mean of that, and then the mean is 3.5, right? So we simply take the mean of that, and then we're gonna find the mean of that sample, right? So like now say that we have a throw a dice 10 times, so it is a single time, right? So we're going to throw a dice 10 times, and the outcomes are 5 2 6 2 2 1 6 1 6, and etc. And we're gonna calculate that mean of that sample, and we're gonna get a, which is 3.0, right? So like the average value is 3.0 with 0.5 distance from the expected value. So we expected 3.5. This is our expected value, right? So means like the variable into the probability value, of that variable. This is our expected value. If you run the 10 times, which we follow the law of large numbers, which we tend to get the average, right? So the average value is 3.0, but we are getting the 3.5, means is like 0.5 distance from the expected value, which is 3.5. The average value is 3.0 and the expected value is 3.5, which is the difference is 0.5, right? So now you roll a die n number of times. If you roll a die in n number of times, and n become larger than you will notice, and the average value will converge to the expected value. So here we have a 0.5. Here we have a 0.5 difference. So if I run 100 times, or if I run 200 times, or if I run 3000 times, and it tends to equal the average value and the expected value, means like the average value is will converge means like it tweaks to the expected value, which is 3.5. Means I am saying like this 3.0 will become the 3.5 if you run the 3000 times or like 4000 times. If we have roll a die for 1000 times or 1 lakh times, and the value which is converge to the value which is our expected value. This is the law of large numbers, right? So the mu, which is mean, is equal to the expected value of that event. That is, we are taken from this law of large numbers. I hope you understand that. So I have given explanation like, so because of the law of large numbers, so as you increase the n, each possible value of p of x will occur with the equal probability of 1 by 6, and that turns to the average of expected value. As I said now, like, so these three, the average value of that probability value will converge to 3.5, which is our expected value. I hope you understand this. What is expected value and what is it telling, how we calculate that. So I just want you to recapitulate what I have said till far. So like we have covered the histograms. So the first we have covered the histograms. So what do you mean by these histograms? Means like it summarizes the data. It is used in both continuous and discrete variables by showing the numbers of its fall from a specific range. Maybe we have this 5 to 10. This is a specific range, right? So I just given a histogram example out there. So I just want you to look at that, and we have a density plot out there. So what is this density plot? It's just a smoother version of that histogram. And after that, if you remove those bins, we're going to get this, which is a normal distribution. I'm going to cover this. What is this bell curve? And what is this normal distribution, and etc. But as of now, just we aim to find the area under the curve. So what is this area under the curve? The area under the curve is integration, right? The slope of the curve is differentiation, and the area under the curve, which is integration. And how we find that? We just simply integral p of x d of x, which is the function, and then we're going to get our output, right? And then we have covered the expected value. So what is this expected value? It's just a measure of a central tendency of a probability distribution, right? So we are expected some value based on the values which we have, right? I have given a practical example over here in the stock market. Like we have based on these two, we expected the value which is the $7 of profit for each share they sell, right? So they are making the 80% making profit of $10, and the 20% of making loss of $5. By these two, we conclude with the expected value of a $7, which is a profit of each share they sell. So after that, we have seen the calculating the mean, how we calculate this mean of the sample, and how we calculate the expected value. And I have given a great detailed explanation over here. So and in our next lecture, we're going to cover the measures of central tendency. So here we're going to cover the mean, median, and mode, and how this median and how this mode, and we have a great detailed talk over there. And we have a quantiles over there, quartiles over there, and how these gonna have, and we have a distribution over there, and we have interquartile range, and we have a interpreting these IQRs and percentiles, deciles, variance. We have a lot more lectures to discuss. So I hope you love this lecture and understand this lecture. So until then, bye bye. See you in the next lecture.